Hello. Our project was to design and build a 3D printed aircraft for UTA's 4th annual 3D printed aircraft competition being held this July. The main rules are that all structural components must be 3D printed, and we are only allowed 5 seconds of power to launch the aircraft and to keep it flying for at least 19 seconds without power. Our goal was to create a lightweight aircraft by using a thin-skinned, stiffened structural design. We accomplished this by creating test pieces to finalize what design aspects work best with respect to the 3D printers we used for this project.
The nature of our project called for a cyclical design process, starting with an initial design based on existing aircraft. From here, we identified our plane's key features and created test prints to learn more about our printer's capabilities and our overall design. Information gathered from these test prints was used to modify the previous design. Our aircraft takes advantage of two different 3D printing technologies. The first is the HP Multi-Jet Fusion 580, which prints the majority of our aircraft using a strong but flexible polyamide 12 powder. The second is the Markforged X7 printer, which allows us to reinforce our aircraft using carbon composite spars running along the wings and aft fuselage.
Our initial aircraft design is based upon our existing RC aircrafts and standard glider plane designs. We started by using OpenVSP to draft our initial aerodynamic structure. We chose a high wing aspect ratio of 23 and chose to taper the wings. We chose a narrow fuselage design and lowered the horizontal stabilizer. A 4.5-degree dihedral angle was chosen on the wings in order to eliminate ailerons. A variety of tests were done in order to test the printer's capabilities for our design. Some of these were comparing HP material and carbon composite material for use as stiffening structures for both the spars and the stringers in our fuselage. Other tests were powder removal tests to see how small a cavity could be before the powder was no longer removable, and wing section fitments to make sure that all the sizes we had designed for each sections of the planes were able to fit together. We also tested for how we could integrate different aspects of the structure in the entire plane.
For the final aircraft design, we utilized a lot of the lessons we learned from test prints to drive these changes. For instance, to facilitate powder removal and simplify the design, we made the wings and aft fuselage uniform or untapered. To account for the aerodynamic drag and stability changes resulting from those wing and aft fuselage changes, we swapped from a conventional tail to a T-tail, lowered the aspect ratio, and widened the fuselage. Additionally, we implemented a carbon composite center spar to act as the primary internal wing structure. We did this because it added the wing stiffness we need when compared to using the HP powder bed printer. And finally, we settled on a push propeller to protect it from potential front impacts when landing or crashing.
Finishing off in the results and conclusion sections, as we've stated, we were able to integrate a composite carbon fiber spar into our wing design, as well as the fore to aft fuselage. In the bottom left of the section can be seen where we've integrated a living hinge into the vertical stabilizer and horizontal stabilizer to act as the rudder and elevator that the push rods and mounts will be connected directly to. Where we can, we've kept modularity in mind and made repeated parts that could be attached together, as can be seen in the top right of the section. Our wing is made up of 4 repeated parts and then the end cap. In conclusion, using these design choices allowed us to choose an aircraft that would maximize its lift to drag ratio. We were able to make parts that were repeated and easily assembled, and the material allows us to get as thin as possible while producing a sturdy part that will not fail.